We might as well begin.
Yeah.
All right, so we're joined by Zach Hartman, who's part of the Alapaki team. He's joining us from Georgia State University, and he's also working at Lowell Observatory. And he's going to be talking to us about wide binary star systems.
Yeah, take it away. Thanks for the introduction. Happy to be here. It's my first time in Hawaii, so it's been pretty great. Just got to go out and go to Volcano National Park and see the craters and stuff. So that was a real blast. So yeah, so today I'm going to talk to you about my research involved in white dwarfs. That was the white dwarf conference next week. Wide binaries, although I do have some wide binaries that have white dwarf in them. So I'm just going to talk a little bit about how these whites are formed, the method we use to find these wide binaries in Gaia DR2. Then I'll go into what I mean by the lobster diagram, hence with the name of my talk, and then I'll go into some other searches that were ongoing, looking for triples, quadruples, and more through other various methods. So on the right over here, I have a picture of a wide binary. Now, some of you, well, maybe not, but if you just look at this picture and I say there's a wide binary in here, maybe you're thinking it's going to be these two bright stars. And it's actually not. So this is the Alpha and Proxima Centauri system. So you have Alpha on the bright star on the left, and then you have, in this little red circle down here, Proxima. So the angular separation between these two is about 2.2 degrees. In physical separation, that's about 13,000 AU. And so if we just look at the general multiplicity fraction of stars in the field, it's about 30 to 50%, depending on whether you're looking at massive stars or whether you're looking at low mass M stars. But across all of that, it seems that roughly 2% of all the binaries are in these wide systems with separations on the orders of tens of thousands of AU. And so what do I mean by wide? So talking about class of binaries with 10 to the 4 AU and separations are greater. So if you look at this plot from Ragavan et al., you have these close binaries down here that have separations less than an AU. Or on the other end, you have these wide systems that have separations on the orders of tens of thousands of AU. And those are the ones that I'm looking at and interested in. So with these binaries, their orbital motions are negligible. So when you look at them on the sky, you're never going to see them orbit. And for the purpose of this talk, when I talk about pairs and identified pairs that we found, we're considering those to all be basically binaries. I'm going to throw out percentages like 95% and 99%, but for the most part, we consider them all, to the best of our knowledge, to be binaries. Maybe with additional information, we'd be able to further figure out which ones are which. And just throwing a number out there, so the typical protostellar core size is about 0.1 parsec. So these wide systems are already on the order of this protostellar core size, and it kind of makes you wonder, how did these systems form? But first, I want to get into the importance of why we care about these systems. I mean, sure, why they form is interesting, but they're more useful to us as tools to answering other questions. So when you look at a wide binary system, you essentially have two single stars, but they're the same age and chemical composition. So they can be used for Gaia chronology, or as shown in this plot right here, you can use it to calibrate metallicity. So if you know the metallicity of the primary, metallicity of the secondary, they should kind of follow a one-to-one line. And so you can use that for, say, a K dwarf or a G dwarf that you know the metallicity of, and say if it has an M dwarf companion, then you know the metallicity of that. On the other hand, these are weakly bound systems, which means that you can use them to examine galactic tides and galactic evolution, but you can also look at machos. And so on the right over here, I show basically a simulation of if you have different sized machos, what happens to the separation distribution of wide binaries. And you see that as you increase the mass of the macho, the separation distribution turns off at a sharper angle. So that's all well and good, but I really want to know how they form, because we really don't know that yet. There have been various scenarios pointed out over the years, and I'm going to go through three of them, the three main ones that I think are the three main ones over the past decades or so. And so I'm going to first start off with this idea of cluster dissolution. And so this was put forth by Cohenhoven in 2012. And basically the idea is you have stars forming in these open clusters. And as the cluster falls apart, two stars either remain bound or they become bound as it dissolves. Now, just right off the bat, this does not appear to be the dominant mechanism, based on evidence from young star forming regions, which I'm going to get into in a couple of slides. So stay tuned for that. And then you have this idea of the unfolding of hierarchical systems. And so this is where three or more stars form in a single cloud, and over time, two of them form a close binary and kick the third out via angular momentum transfer. And we can already see this happening in young star forming regions based on this picture from Alma from Tobin et al. In 2016. So you see the three components, and maybe in a couple million years, that third component would be kicked out even further. So I talked about this evidence from young star forming regions, and the basic idea is this. So we've done these analyses of like beta pic and the TAR star forming region, and we found that once you get out to extremely wide separations, most of these pairs are triple systems. And this seems to point towards the unfolding of triple systems as the dominant mechanism. But the ages of these different star forming regions tend to point towards that not being the case, because it takes a really long time to unfold a triple system. And so if that's the case, then there's something else going on. And so in 2017, we had this new idea from Andrei Tokubin, where stars form in adjacent cores inside a star forming region. They're kind of protected, shall I say, based on their gravitational, because they're gravitationally bound in the star forming region. But you have this huge excess of pairs at these large separations that then over time, you have most of these pairs just getting broken apart via interactions with other stars in the cluster or other stars in the star forming region. And then eventually it forms the smooth distribution that we saw in Ragavan et al. So how do we know which of these is correct? Because there are three different ones. The unfolding of triple systems tends to point to wide binaries with very eccentric orbits. And we don't really see that right now, but that said, there's not a lot of data on eccentricity, which is why that's on this list. So how do we determine which one, if any, is correct? So we look at the higher order multiplicity. Right away, you would expect the unfolding triple systems to mean there would be more triple systems via that method than other ones. The other two, the cluster dissolution and the adjacent cores, they highly depend on the environment. So if you are in a dense star forming region, you're not going to have that many wide binaries in the first place. And so this has already been.
All right, quick question. So when you say the unfolding of a triple system,
Mm-hmm.
you mean the wide binary? There is the wide binary that is seen the leftover inner pair, or is it?
No.
What you're actually seeing is that it looks like a wide binary, but it's really like a hierarchical triple.
Right. So what happens is you have a triple system form in a single protostellar core,
Right.
And then as the interactions occur and you form a close binary with two of them, it kicks the third out. And so, I mean, you may see the close binary as a resolved double, but if that was the case, then it would have formed. You would have had a weird formation scenario to begin with. So yeah, so looking at the higher order multiplicity fraction of these wide binaries, so seeing if they're triples, quadruples, or more, is some way that we could at least kind of understand. I don't think it's going to be the deciding factor. It's not going to be like if we know the higher order multiplicity, the higher order fraction, it's going to be like it's this case, but it will help us. And then examining the distribution of projected physical separations of triple systems, particularly that inner orbit. So if the inner orbit separation, if we look at a whole bunch of these triple systems and we see that the inner orbit is closer than what we think, should we normally, so like for an M door, for example, The common separation there is about 10 AU. Let's say for wide binaries, wide M-dwarf binaries, and triple systems, the separation is 5 AU. That may indicate something. And then, as I mentioned, eccentricity probably will help us a lot in determining and narrowing down the options of wide binary information, but it's really hard. You need a lot of statistical data, and maybe with Gaia, there's been talks about maybe Gaia DR2 will allow this to happen, but I haven't seen anything on that. So how are they found? I've been mentioning Gaia DR2, and that's really the way we find these wide binaries. We look at large databases of stars, and Gaia's the best right now. So what we do is we look for blinking stars. And what I mean by that is you have 2 epochs of observations, or you have proper motion, so you get proper motions basically. And so you're able to see that all the stars in the background remain in the same location except for these 2, which are moving in the same direction. And this is DJ 362 and 360. And so the way we find these pairs is through a combination of angular separations, proper motions, distances, and radial velocities. The most common over the past decades has been angular separations and proper motions. There have been a couple surveys where they look at angular separations and distances. And normally what it is you need angular separations because you don't want to say, okay, here's a star this side of the sky, and then there's one over here. They're at the same distance, but they're a couple 100 degrees away from each other. So you need angular separations, and then it's just a combination of the last 3. So just going through a few of the previous searches. So Lapine and Majoro in 2007 took the Hipparchus catalog and looked for companions this way, and they found 521, and they found that roughly 10% of nearby Hipparchus stars have a wide companion. And that's kind of been what we've been seeing as well. And so on the right here, you have their physical separation distribution with a couple of models fit to it. In their paper, they found that the separation distribution of the wide binaries does not follow OPEC's law that well. There's a little deviation to it. And then the other one I want to highlight is the Slowpoke survey from Detal et al. In 2010 and 2015. These used SDSS. And so Slowpoke 1 used proper motions, angular separations, and photometric distances to search for their objects. Slowpoke 2, on the other hand, just used angular separation and distances. And as you can see, this has a huge effect on what the separation distribution looks like when you ignore proper motions. And so for Slowpoke 1, it's kind of like goes up and then it plateaus and then it goes down. Slowpoke 2 just kind of keeps going. And we'll get into this later on, but we believe that most of these in Slowpoke 2 are most likely chance alignments because at the super large distance, I mean, you're at 10 to the 5, 10 to the 4.5 AU, you start to see, if you're looking at lower probability pairs, chance alignments in Gaia DR2, you get a peak roughly around there, and that's why we think that most of those are chance alignments. So creating this catalog, so what we did was we looked at Gaia DR2. So I'm working with Sebastian Lapine at Georgia State, and his big thing is high proper motion stars. And so that's why we looked at stars with proper motions greater than 40 milliarc seconds. There's another reason for this. If you have high proper motion stars, the likelihood that you have another star nearby that has the same proper motion as it decreases as you go up in proper motion magnitude. So if you have a star that's moving with 1,000 milliarc seconds proper motion, and there's another one right nearby it that has 1,000 milliarc seconds, it's probably a wide binary. So we take these stars, we get roughly 5 million. We combine this with the SuperWide Catalog because Gaia has this issue with high proper motion stars itself, where it misses some of them. And also, if Gaia thinks something is a binary, or it sees a double-line spectroscopic binary, it doesn't include any information in it in the catalog. And so we took the SuperWide Catalog, which was just proper motion, but there was no spectra really involved in it. And we added this in the hopes that maybe we'll find some other companions that Gaia right now doesn't list. And so what we did was we took the angular separations, proper motion differences, and the distances and the distance differences to figure out our probabilities. So I just want to walk you through how we did this and kind of give you a sense of why this method works as well as it does. So on the left-hand side here, you have just a patch of the sky and galactic coordinates, so L and B. And let's say we have a star that's right here. So it has this kind of uniform area that it's looking at, where it has this uniform distribution of other stars. But when you go to the proper motion, so this is proper motion L and proper motion B, you see that things are very different. So let's say our star has a proper motion that places it here. Then there's not many stars around it that are potential chance alignments. So we go to the next slide and we change the location of our star. You can see now the proper motion location really has a lot of contaminants in there. And we need to eliminate those contaminants. And then if you move it some more, you get to see that, yeah, there are certain areas on the proper motion plot where it's easier to identify real pairs. So we look at
just a question. So
yeah.
What is the circle, the red circle on the right?
So the circle represents our search area. So you don't want to, when you're doing the search, because there are so many stars, you don't want to compare, say, this star here to this one down here, because it's just adding so much more computational time.
But on the right, how do you choose the size of your search area?
So the size of the search area over here, we pretty much, so based on previous searches, we knew that roughly most of the real pairs will have proper motion differences around the order of 10 milliarc seconds. In order to just make sure that we grabbed everything, we went out to 40, which adds a lot of computational time, but it also allows us to characterize everything really well. So that's where that circle came from.
What's the proper motion uncertainty?
So the proper motion uncertainty in Gaia is, on the faint end, I believe it's 1.2 milliarc seconds. And then as you get brighter, it decreases to, I believe, like 0.4. So
Naively, I would have expected the search circle in proper motion space to be, whatever the 3 sigma or 5 sigma proper motion uncertainty is.
yeah, and when we look at the real pair distribution, that is what we see. So we overestimated it, but we also were just making sure we got everything. And one of the reasons we also did it is because as you get closer, tangent or the velocities in between stars. So if you have a star orbiting each other, then that starts to play a role. And so we wanted to see if we could grab those as well. So that's why we chose it to be so big.
Is there a reason? I imagine it's computationally very complicated. Is there a reason that you don't just convert to galactic XYZ UVW?
So actually, so what we do is we start out in our index, and then we convert that into XYZ. And so when we do our search through and we compare proper motions and positions, that is initially what we do. We use our index XYZ, the Cartesian coordinates of that, in order to determine the separations.
So you can imagine if things are actually quite close by and headed in the same direction, that they could appear to be the projected direction of the proper motion could be quite different, even if they are traveling parallel.
Yes, and so that's a worry of ours, but at the same time, we think that our code takes that into account. That said, we haven't rigorously tested it in that way, but as we'll see later on, we do have the majority of our stars are between like 100 and 500 parsecs, and out there, it's not, that doesn't matter very much. So I'm just going to walk you through our process for the angular separation and how we determined our probabilities for this. And then it's pretty much the same for the proper motion differences and the distance differences. So what we did was we examined the angular separation distribution in this case. And so you can see I had this rising, basically linear, although in some of them, and some of the plots I was looking at, it does become, parabolic, but I believe that's more due to selection effects than anything. You have this linear rise right here, which represents chance alignments. And then in this corner down here, you have this little peak. And that represents the real pair distribution. And so we need to figure out, in order to do these probabilities, we need to get a model for the chance alignment, we need to get a model for the real pair. In order to do this, what we do is we take this idea that was first pioneered by Lapine and Buongiorno, where they took their catalog and they basically said, all right, we have a star, we're going to shift the catalog by a degree in declination, and this randomizes the area where it's at, and randomizes it in proper motions, in angular separations, and in distances. So when you do that, and you look at the angular separation distribution of these randomized pairs now, you get just the linear rise. There's no peak down on the bottom. And so this right here represents our chance alignment model. And so we take this, we go back to that previous plot and subtract it off. And what you get is this real pair, the residuals, which represent the real pair distribution. And so in the end, we have our two models. We have the chance alignment, we have the reals, and so we're able to plug that into the probabilities in order to figure out which ones are actually real wide binaries. And so we're able to do this for the proper motions and the distances. For the proper motions, however, we did have to do one thing. So when we went to the random catalog and we examined the distribution of the differences in proper motion, so this is differences in proper motion L, differences in proper motion B, it just looks like this mess. And when we went to other, when we examined maybe, so this is actually from one part of the sky. If we would go to another part of the sky, it's something completely different. And yeah.
Sorry. How big? So sorry. If you can go back to the previous plot, or actually keep going one more. Yeah, one more actually. So sorry. That one is all the separations between just random separations between random stars, right?
So no. So this is if we take stars in a certain area, which so for angular separation, we took all stars within 1 degree of our target star. So we examine, so if you have a target star and there's a star within 1 degree, then it would show up on this one.
Okay.
So they're not called by proper motion matching. It's just everything.
There is a, so yes, so the proper motion, so there is a proper motion difference as well. So in this plot, what's in this plot actually, and I'm sorry, I should have explained this better, but we have two criteria. The separations, angular separations have to be less than 1 degree, and the proper motion differences have to be less than the 40 milliarc seconds that I was talking about earlier.
Okay. Because I was going to say, like, well, since you're looking at the difference between the angular size between one star and whatever 10,000 stars,
right?
I would expect a very parabolic shape just because it's an area as you're.
Yeah. Right.
Okay.
Yes.
So there's a proper motion cut. Got it.
Yes.
Okay.
My apologies. Yes. And so those same cuts are applied here as well. But when we looked at the distribution of the proper motion differences, we couldn't really fit anything to it. It was really hard to. So what we decided to do was we just said, all right, if we have a star, or if we have a certain pair of stars and it lands right there, then that's its probability. So whatever the number of pairs in this box here divided by everything in this plot, that's the probability of it being not a binary. So that's for the chance line. So what we do in the end is we have this giant Bayes equation, basically incorporating the angular separations, the proper motion differences, and the difference distances. And when we go through and we calculate the probabilities for each star, we have two conditions. So we require that the primary G magnitude be brighter than 19, and that the parallax errors be less than 10% of the parallax. So the primary G condition was brought about because if you go less than that in Gaia, there's this weird effect that starts to happen in the proper motion distribution of stars where an X kind of just appears. And most of this is because of problems in the galactic center, where the proper motions are really funky. But we decided that just for the sake of making the analysis somewhat easier, we were just going to cut it at 19 and move on from that. And then the parallax errors were just because we didn't want stars that had like really like 70% parallax errors that, in essence, you don't know what the parallax is. Yeah.
Good question. So when you do it, the cut in G,
Yeah.
What percentage of stars are you cutting out,
I don't know.
roughly?
I don't know the answer to that off the top of my head.
No problem.
I can tell you that I can tell you the remnants of the cut. It's 800 million possible pairs is what survives that cut.
Okay.
And because I implement the G cut basically right in the beginning. So yeah, sorry.
No, it's okay. Yeah.
When you say primary, does that mean that one of the stars has to be brighter than 90th
Yes.
magnitude?
Yes. Yeah. So I'll talk about this later on because I do change the definition of what I call a primary and secondary. But for this initial part, primary is the brighter one because we have no masses for them. Yeah. So with that, run it through these probabilities, and we get the SuperWide Catalog. And so we get 99,000 possible pairs, so wide binaries with probabilities greater than 95%. Their angular separations range from a 2-degree cutoff to 1800 arc seconds. Not 2-degree, 2 arc second cutoff. And the reason for that 2 arc second cutoff is because if you look at the angular distribution of the stars in Gaia, you can see that roughly at 2 arc seconds, the distribution starts to turn over as Gaia does not resolve the companions that are there. And so that's why we chose 2 degrees. We have some stars with distances beyond 500 parsecs and physical separations out to a few 100,000 AU. And you can see that we have an all sky catalog. So just to prove also that this catalog is even better, we took the stars that were both components had radial velocities. And we plotted them over here, primary RV versus secondary RV. If they are a real pair, we expect these RVs to be roughly the same. So they should follow this one-to-one line, and most of them do. We also plotted out the radial velocity difference, so the primary minus the secondary, as a function of physical separation to see if there's any biases that we're having, any discrepancies. And it looks to be okay. If you take the stars that are outside, so these 2 lines right there represent the 3 signal lines. If you take the number of stars out there, it comes out to roughly about 11%. So we have a contamination rate naively of 11%, but if we exclude all the stars that have RV errors larger than 3%, then our contamination rate drops down to roughly 4%, which would be consistent with us saying that our probabilities, these stars have probabilities greater than 95% and up. So here's the 2 plots that show the projected physical separation. So on the left, I show the distance, and so this just kind of shows that most of our stars are between 100 and 500. And then physical separation on the bottom. These 2 red lines here represent our cutoffs, so our 2 arc second cutoff on the left, and then our 3600 arc second cutoff on the right. And then here's a plot that kind of, so I mentioned earlier that we don't believe in the Slowpoke distribution that those stars that they have this giant peak at 4.5 log separation of 4.5 is real. And so this is kind of what we hope to prove is our proof that that is indeed the case. So the green distribution here represents pairs with probabilities greater than 95% and up. And you can see that there's a single peak at 10 to the third or 10 to the 3 AU. And then the yellow distribution represents a kind of intermediate group between 95% and 20% probability. And you can see that even though there are stars or pairs everywhere along this, the majority of these pairs are out at these large separations. And it gets worse when we go to even lower probabilities, which is shown by this black histogram here. And you can see that the vast majority of the pairs being added in this probability range are in this 10 to the 4, 10 to the 5 area. So we believe that in the Slowpoke data, at least, most of those pairs are most likely chance alignments.
Quick question about
Yeah.
the previous slide. So I gather that's in meters per second.
Yes.
So the RVs, well, I mean, because if it's in,
Kilometers per second.
Yeah, I think Gaia gives it in kilometers per second.
oh, okay.
That's fine.
Yeah, that's quite fast. It's quite zippy. Yeah, I guess there are these like really excessively fast-moving stars.
Yes.
So I guess the cloud there is reasonable for, so some of those are going to be actually spectroscopic binaries.
Exactly.
Is that
That's
the belief?
well. So in Gaia, if they're detected as double-line spectroscopic binaries, they aren't included in the catalog. So we think some of these are just going to be regular single-line ones. So yeah.
Okay. So yeah, you would kind of expect to see that. Okay.
And as I said, if you if you put an error cut on the RVs, that cloud kind of really goes down. Because most of these stars out here have, because maybe they're spectroscopic binaries, they have high errors in their RVs.
Okay. Yeah, the other thing that I was thinking was that, you know, if you're restricting yourself to a region of the sky that's within a degree, I mean, I guess you kind of do expect them to have pretty similar velocities just because of the spiral motion of the galaxy. Like if you look at an all-sky plot from like Rave, for example,
Yes.
you'll see like a trend that way.
Yeah, but so that is true. And if you take stars that have if they have a really low probability for my search, it's a very puffy thing, but it does still look like they're correlated.
Yeah. Okay.
Although going to the physical separation plot really helps in identifying which ones they are. So here's the HR diagram, or not HR, color magnitude diagrams, my apologies, of the primary and secondary stars. So you can see that we span most of the spectral ranges. I don't think we have any O stars. I don't believe so. So the majority of them, though, are K and M dwarfs, mostly because we're doing a proper motion limited survey. You can also see from the secondary diagram that we're dealing with an unclean sample of Gaia. So if you go through, so there's a paper by Lindengren about the Gaia catalog, and they include a bunch of criterion that you could add to make a clean HR diagram. So this includes taking into account their excess error, the error in the magnitudes, and the error in the parallaxes in order to clean out this little area right here where you see a bunch of stars. I don't believe that these could also be white dwarf M dwarf pairs, unresolved systems. However, I don't believe that because there's way too many stars in there. So I think most of it is because we're using an unclean sample. Now, the thing that I want to draw your attention to, and that I'm going to be spending the next couple of minutes talking about, is the area within the K dwarfs. So this is where the K dwarf region is. And you can see that there is a doubling of the main sequence. This doubling is because of unresolved companions basically causing the component to be overluminous. So that's what the rest of the talk is really going to be about, is the search for triples, quadruples, and more using this overluminosity idea. So if we zoom in on the K dwarf region, the red box kind of is the area of the K dwarfs. You can see that there are two parts. You have this main sequence here, which represents the single star main sequence, and then you have this overluminous double main sequence here, where most of those stars are most likely overluminous because of an unresolved companion next to them. And so this represents possible, because we're dealing with a catalog of wide binaries, this represents possible triple systems and quadruples. And so I went in and I took all the K dwarf binaries that I had. So we have 2,227 K plus K wide binaries. We increased the probability cut to 99% and limited the distance to 250 parsecs. And here, as I was talking about earlier, we switched the definition of what a primary and secondary is. We switched it to be determined by color instead of magnitude. This was to make it easier to deal with in the second part of our analysis, which I'll get into in a bit. And so what we defined was an overluminosity factor. And what we're defining it as is you have the absolute magnitude of a component. Let's say it's here. And then we have this dividing line, this yellow line that's basically cutting the main sequence, single main sequence from the double main sequence. And if you take the difference between the two, between the absolute magnitude of your component and the absolute magnitude of the line, whatever color it's at, you get an overluminosity factor, basically saying how overluminous something is. And if it's negative, then it's going to be overluminous, and if it's positive, then it's going to be within that single star main sequence. And so what you get is the lobster diagram, which is a comparison of the overluminosity of the primary on the y-axis and the secondary on the x. And as I was saying, negative overluminosity indicates that the component is a possible unresolved binary. And we call it the lobster diagram because you have the body of the lobster, and then you have these two little claws right here. And so what does this all mean? And so I'm going to highlight 4 areas of interest. The first one is the body of the lobster. So this one-to-one apparent line that goes from a little bit less of 0 all the way up to all the way wherever the plot exists. And this is where both components are single stars. So they both lie in the single main sequence of the color magnitude diagram. So if you're looking at the color magnitude diagram, you're below the yellow line at this point. The purple region represents an area where both components are unresolved binaries. So they're both overluminous. They're both in that double main sequence above the yellow line. The 2 yellow regions here represent an area where one of the components is overluminous, and hence we think it's an unresolved binary. If you go below the one-to-one line, these are where the primary is the overluminous component. Over here is where the secondary is overluminous. And then these 2 red dotted lines here, these 2 red dotted line regions, represent areas where a equal mass unresolved binary would exist. So essentially in the claws of the lobster. And because we see this over density, which is frankly fascinating. And so if you calculate the numbers and everything, so we started out with 2,227 wide binaries. And this is how the breakdown occurs. So you have 1,300 true wide binaries, where both of them are identified as single stars in this diagram. 450 with an overluminous primary, 340 with a secondary, roughly 100 quadruple systems. And if you total all of these up and divide it by the total number of pairs, the 2,000 number, you get an overall higher order multiplicity fraction of roughly 40%. And so this is interesting because that's roughly what is probably going to end up being the multiplicity fraction of K-dwarfs. If you think about it, the solar type stars have roughly around 50, the M dwarfs are around 28-ish. And so if we're just drawing a straight line between them, the K-dwarf should be roughly around that 30 by the 40 regime. Now, this makes no sense to me because there's no physical separation, protective physical separation cut here. These pairs range from hundreds of AU to tens of thousands of AU. So there's no reason why this should map to the multiplicity fraction of single stars in any case. Now, if we go back and we select the stars that have separations greater than 10,000 AU, so that's these red triangles here, and you total those up, you get around the same higher order multiplicity fraction. And this at least seems likely to me because now you're dealing with essentially 2 systems that are not interacting at all and may have formed from similar or adjacent cores to each other, so not pulling from the same material. And that at least kind of makes more sense for why it may be closer to the single star multiplicity fraction than what? Oh, all right. Than the other group that I was talking about. So, yeah.
I may have missed it. Just how would you define overluminosity?
So overluminosity is the absolute magnitude of whatever component we have minus the value of this line at the color of the star. So there's a yellow line going through the middle of this plot, separating the single star main sequence to the double star main sequence.
I'm just curious, how did you decide on where that line goes?
We just drew a line.
So it's not a fit?
It's not a fit. And if you notice down here, as you get closer to the M dwarfs and as you get closer to the Gs, it underfits it.
I was curious why it's not in the middle of the bulk of the stars.
So I mean, we kind of fit it to the point where it was the straightest, where the main sequence was the straightest, which was in this area here. You could put this line anywhere. You could put it down here, and you would still get the same result.
Yeah.
So yeah, it's an arbitrary line.
Okay.
So
okay. So that explains why on your next plot, the main concentration is not centered at 0, 0.
yes. So if we had a perfect line, this would not dip down into this area here.
So on that previous slide,
This one?
sorry, yeah. So I was trying to see the degree of overluminosity. So it's about a magnitude on either side. So it's like it's a factor of 2.
It is 0.7.
Okay, so it's a factor of 2 in brightness. And so is the idea that this is caused by having 2 stars? Or is it caused by, the other thing you can imagine is that binary motion inflates the parallax measurement, causing you to believe the object is closer than it is.
I hadn't thought
Right.
of that. So we believed that it was due mostly to, because even though these are at like 100 AU, maybe separation, and they're still like 2 arc seconds apart from each other. So Gaia should be able to resolve that with ease. And so I don't know what the parallax inflation would affect those stars. Now it may affect it if there's another close companion. So if you do have another triple.
Right, I'm just saying, like, if you had a, I mean, so I guess Gaia's resolution is at, whatever, an arc second level or something like that
Mhm.
but you have milli-arc second separation between the components, say.
Well, if that's the case, if there's a milli-arc second binary, Gaia is never going to resolve it. And in that case, I would consider that an overlumin. If they're both roughly, let me rephrase it. If the secondary of that system is luminous enough where it contributes light, then I would expect it to be in here. And I don't know whether or not the parallax error on it is probably higher, because Gaia would only have a single parallax, and the error would probably be higher because it doesn't have a great fit of the PSF. But I still think it would be in this area.
Yeah, I only ask because I'm actually working on trying to get stellar parameters out of an eclipsing system that has a reported Gaia parallax of 1 milli-arc second, and I have a Chara resolved binary separation of 3 milli-arc seconds. So like the stars are, and the horror of this situation is having to figure out and knowing the direction on the sky and looking at Gaia scan angles to figure out whether or not it would have been confused as a function of time about where what would it have actually measured, and would it have inferred that was due to Earth's orbital motion by accident?
I mean, I would look at the error. I would look at the parallax error. If the parallax error is larger than like 0.4 milli-arc seconds and it's a 1 milli-arc second parallax, that's your key thing that it's like, this is wrong, but yeah.
Yeah, it's interesting that the presence of, I guess, both star, like, so if you had orbital motion and they both go the same way, then the sign of the error goes the same. It makes it brighter both. So
yeah,
makes it easy to be overluminous.
yes. And I haven't looked into whether parallax overinflation is happening in these.
I don't think really anybody has.
No. So yeah, so we have this higher order multiplicity fraction overall for all the K dwarfs, and it was around 40%. But we wanted to look at what happens as you go across the K dwarf region. Wrong way. And so what we did was we redid this entire analysis, and we split the K dwarf region into 4 equal bins, bins of equal color. And so that's what these dotted red lines represent. So we split into these 4 equal color bins. And what we did was we required the primary. So we remember we are now calling the primary the one that is bluer. We require the primary to be in one of these bins. The secondary could be anywhere in this red region. And so, for example, you could have a primary here, but a secondary down in this region. But if you had a primary in this region, you could not have a secondary up here. And if we do this and we recalculate the higher order multiplicity fraction across those 4 bins, we get a decrease as they go across. And to me, this also indicates that it is like the single star multiplicity fraction, because this is kind of what I would expect naively. What would happen as you go down the K-dwarf region, going from a higher order multiplicity rate or multiplicity rate in general to a lower one. And we don't really see any biases against this being the case, besides the fact of what I was talking about earlier, where the physical separation of these pairs can be anything. And so we're still trying to figure out what this result actually means. So yeah, so that's my overluminous search through Gaia, and that's kind of what you can do with the Gaia data. Because once you get down to, as we were talking about, milli-arcsec separations, Gaia doesn't resolve that. You're not going to see any binaries in Gaia with that. And Gaia actually has a bias against binaries with separations less than 2 arcseconds, because it doesn't pick them up, or if it does pick them up as a double-line spectroscopic binary, it's just not in the catalog. And so what we do is go through other searches and take observations. So part of what I'm doing is doing spectral imaging. So we're building, I'm right now at Lowell Observatory working with Gerard Benvell, building another spectral camera there to go on the DCT. And I had a proposal for Alapeke here this semester, looking at halo wide binaries, determining if that higher order multiplicity fraction is different than, say, the disk wide binaries. And so we're following up on that. We're doing radial velocity studies. We have some time on the 1.5 meter. I had some Hydra data taken. Have taken some Devaney spectrograph data from DCT right now. But in the end, Gaia is going to release all the radial velocities in the world, so that will help immensely. And then also test. This is an interesting part that I hope to do more work on. So just from comparing my catalog to the test input catalog, there are about 12,000 pairs in it, and there are probably more that that are in the full field, the full frame images that I just haven't looked at yet. This was a previous slide from looking at something else. So this is why cycle 2's in here with 2600 in the Canada target list. So we're going to have a lot of them with the high cadence stuff to test. And eclipsing binaries is also another way to look at how these systems formed, because let's say you have a higher number of eclipsing binary systems than in the field, that could tell you something interesting about their formation. And then just to end the talk today, I'm just going to show you some initial light curves. So here's one of the binaries in test. It has a period of about a day. And then also there are some spots on it, as you can see, with the modulation, the sinusoid modulation in the curve up top. Here's just another one that I have done no analysis on, and I have no idea what it's doing, but it looks cool, so that's why it's here. And with that, I'm just going to conclude and say we have this catalog of 99,000 high probability pairs. We have a bunch of them. So one thing that I did not talk about in this talk is that there are a bunch of stars in Gaia that have high parallax errors, that don't have parallaxes, etc. We went through, we did, and we have another catalog where we only use angular separations and proper motions. So we have a catalog of around 60,000 of those laying around if anybody wants to use that. So yeah, thanks for having me. Yeah.
One kind of general question I had was, I don't think you maybe touched on too much, is you had a lot of different selection methods to analyze your data, which we all have to do. But what kind of, in general, biases would you expect from your different kinds of cuts that you have to make for different reasons?
So the parallax cut is one where it would definitely cut down on the number of unresolved binaries that I would get from Gaia. Because if Gaia, so let's say there's a equal mass binary, close binary that has a separation of like 0.4 arc seconds, and Gaia doesn't detect it, then what's going to happen is the parallax, but it detects one of the stars, then the parallax on that star is going to have a huge error on it. And so by including the error that I did, I'm effectively cutting that star out. But I'm hoping that secondary catalog takes care of that bias. That was actually, so in terms of the catalog, there's not many biases that I can really think of off the top of my head in terms of the analysis, just because we went for more of a complete sample, just include everything, even if it will turn out not to be a binary. In terms of the lobster diagram and the overluminosity, I have no idea. I've been thinking of it for like the past month, and I have no idea whether there are any biases in that. So.
Interesting. Okay.
Yeah, I don't know of any big biases right off the bat. Besides the fact that Gaia has a bias against close binaries. That's the only thing.
I guess one thing I just thought of was you can probably play around with like the because you have a dividing line on that plot. What would happen if you move it slightly down or slightly up?
Well, so yeah, so that's what
I
I don't think it would change anything because it's just an arbitrary line. There's no, I mean, when you look at the lobster diagram, what would happen is it would just move up and down depending on where you move that line, or up and down and left and right. So I don't think that would affect it that much. And in fact, one of the things that we want to do is expand that to the M dwarfs. And my idea for how to do that is we have one of my fellow grad students at Georgia State who's working with my advisor has taken my catalog and compared to the Apogee. And so we have the metallicities of roughly, I think it was like 20,000 primary stars. And if we assume that my catalog is right and the secondary should have the same metallicity, we have a map of the M dwarfs where we could effectively just continue this line through the M dwarfs. So metallicity may be an answer to that question. Like if we draw, instead of putting the line in a single spot, if we require the line to follow the metallicity lines that are in the K dwarfs, that could add something to it.
So you showed a very nice plot of the radial velocity of the star 1 versus radial velocity of star 2, and you get this nice line. Do you have a similar plot for proper motion of the primary and versus secondary?
Yes.
That gets back to this question of
let's see if it's in the back of this. Yes. So, so this is delta proper motion L, delta proper motion B, where it's primary minus secondary.
right.
And so, as you can see, it's really just right in the middle is where.
So your cut could be.
Oh yeah, it could have made my life so much easier. Instead of taking 8 hours to run the code, it could take 4. So.
Yeah, it's really tight.
Oh yeah, I mean we could have. But so one of the reasons I did not want to go down that far is because when you cut, let's say we cut it down to like 10 milliarcseconds on either side, you wouldn't see the distribution, the chance alignment distribution the same way. You wouldn't be able to effectively model out what's going on. So that was another reason why I did large things. But yeah, it would have made my life so much easier if I had done like 10 milliarcseconds.
So you didn't really find anything beyond 4 milliarcsecond separation based on this plot? Or sorry.
Yes, based on this plot, yes. I mean, there's variations as you go out. Roughly because
Oh, sorry, this plot is 40 versus 40. 40
yes, 40 milliarc seconds.
plus or
Per
minus,
year.
it's 80. It's actually 80.
Yeah. So
and
it's plus or minus 40,
Yeah.
plus or minus 40.
But everything is sort of in there, and
Sort of in like plus or minus 5.
Yeah.
So yeah, like I would hazard a guess that there is nothing out in this cloud.
okay. Yeah, it's a little hard to tell with the stretch, but
Yeah.
So you talked about everything in terms of primary and secondary.
Mhm.
But did you find any that were tertiary? You know, there were 3 or 4 or
Yes.
5.
Yes. So I don't know the exact number. I know they exist because I was observing one last night through the speckle queue. But yeah, there are resolved triples in my catalog. I don't know whether I have any quadruples,
Right.
but
So, strictly speaking, is there evidence that these are gravitationally bound stars, or are they just sort of a moving pair?
so my criterion is that they are just moving together. So they are a truly
That's your
common proper
selection.
motion pair.
That's the selection criteria.
Yes.
Yeah.
In 50 years, if we go back and take an observation of them, maybe.
Then you'll find out.
But these, if you have a pair that's on the order of like 100 arc seconds, and it's 100 AU away, that's 10,000 AU, and its orbital period is on the order of hundreds of thousands of years at that point. So I don't know whether you would even see orbital motion then. And that's kind of the key thing that they bank on with finding these wide binaries through a statistical method, is saying they're not going to rotate around each other. They're just going to keep going. So.
Okay, so you did find a handful of 3 groups of 3.
Yes. Yeah.
Okay.
Yeah, and for those, I mean, because of the separation limit or because of the decrease in resolution, or the decreased efficiency of Gaia as you get closer and closer to 0 arc seconds, the number significantly drops. So.
I should have asked this at the time. Could you go back 35 slides? So it was right back at the beginning, and you said something about machos, and I didn't have time to think. About
Yep.
it. So what was the argument there? That one, yeah.
So the argument is, if you have these wide binaries that are forming,
Mhm.
then if you have these perturbers just sitting around that you can't see, and the wide binary should be affected by them as it goes by. So depending on the mass of the machos, then the maximum separation that a wide binary can achieve would be affected. So with more massive perturbers, you have a sharper separation, or a sharper decline in wide binary separation. So up here you have, if it's a 10 solar mass perturber, and then as you go down to the bottom,
Okay.
you get 1,000 solar masses.
Okay, I get it.
So.
Whereas you don't see this.
I have not looked at it, and I leave that up to other people who are interested.
Well,
in
wait. So what's being plugged here? Some interactors isn't just a number of binaries, right? So,
Yes,
Yeah.
yeah.
So,
and this is a simulation. This is not.
Sure. Yeah.
What you really need to do is see one.
Right.
You need to watch for 50 years and see a wide binary become this, right? Like
Well, yeah.
falling apart.
Right.
And you get, oh, there is something.
Yeah. Yeah, I know Tsunami has been working on this for, what is that, decade and a half already. Yeah, he's been looking through SDSS. He was part of a search through TGAS looking for wide binaries for this purpose. So.
I had another question about you go to the tests Make sure that you jump back
Yeah,
and
I
forth
know,
over
right?
menus. I'm not going to order these. There it was. Okay, if you go back to that one. So one comment that I had was, I guess that might in fact be a spot. At the beginning, it looked like almost a reflection.
Yes, that's.
But,
I got excited when I saw this, and I was just like, "Yes, the reflection effect." And then I got to the second half, and I was like,
no.
"No."
Yeah. Okay.
What do you mean, a reflection effect?
So a reflection effect is when you have two stars of fairly unequal luminosity, and one of them heats the other one. And so, like, one of the stars is basically hotter on one side than the other.
Yeah.
And so, right when the sort of wimpy star goes behind, you're seeing the hot side of the wimpy star just before the eclipse happens. Right. And so, it's basically the same thing as the infrared phase curves of secondary eclipses for exoplanets, where you see basically the hot side of the planet. Yeah. So at the beginning, it kind of looks like the peak. Yeah. The comment that I was going to make about TESS is that if it keeps on doing the way it's doing now, with one sector at a time, you're sort of restricted to orbital periods of 10 days or less.
Yes.
For eclipsing. I mean, you might be able to see. You could also potentially see beaming effects and other things. So it might actually be worth taking a look at the TESS light curves anyway, even if it's not necessarily eclipsing. But and the thing that I would point out is that there are other transit surveys that have been going on for long periods of time that don't have the 28-day window, and so. And some of them, including the one that I work for, are releasing light curves, and they're available like through Nexi.
Okay.
And so you can actually, if you go to, there's like full sky data like HatNet and Kelt and SuperWasp, and you can get data for lots and lots of these things spanning years.
Right.
And so in that case, you're able to detect eclipses that happen over a much wider range of periods, and it might be a useful part of parameter space to explore.
Yeah. So the only reason that I decided to go through this is because, are you familiar with Light Curve?
The piece of software?
Yeah.
Yeah.
Yeah. So that's the only reason I did this, because I could just tell the computer to search mast and do this. And I could go do other things.
Yeah. No, I get it. Yeah. It is important to make it available. That and easily accessible. That truth is not lost on some of us.
Yeah, I mean, would I love to go through all these wide binaries and just get everything for them? Yeah, but it's just at a certain point, I'm like, I want to graduate versus spending another year going through a bunch of light curves. So
the other potential issue is the test might not go as deep. The test definitely doesn't go as deep.
Yeah, it does not. No.
Not even close.
No, that's why I was frankly surprised that I saw so many in the input catalog. But then I was like, oh, they're everywhere. So, but yeah.
Okay. No more questions? Well, thanks very much, Zach.
Thanks for the input.
We'll wrap up.
All right.